In the previous video, we've talked about how to read a typical Vernier calipers and just like one that has no errors or anything like that. However, there are some cases where the Vernier calipers may have a zero error, and in those things we gotta make sure that we take that into account when giving the final reading. So that's what we're going to be talking about in this video. So let's first start with what exactly is a zero error. So a zero error is when the measuring instrument shows a reading even though the true reading is zero. So for example, the device that measures current is called an ammeter. And let's just take a simple circuit right here. This is the ammeter A. And let's just say that there's a light bulb here. There's a switch and a battery or cell. So when the ammeter is here and the switch is open, that means the circuit is incomplete, right? This is incomplete. And hence there is no pathway for current to flow through, which means that the current flowing through the circuit is zero. So for a correct ammeter with no zero error, the reading would be zero. So reading in this case would be zero. When you close the switch, so when we put this down, let's just say that this is a switch and you put it down, you closed it. Let me just write that in red. So that suppose we're in this case right here, the second case. There is a pathway for current to flow through. So current would flow through the battery and through the ammeter and then, through this light bulb so that the light bulb will glow. So in this case, we know that current is flowing through the circuit, and hence the ammeter will show the reading of the current, right? This is how a typical ammeter works. That's how you get the reading. However, for some ammeters with a zero error, even though the circuit is incomplete, in this case, the open case, and there is no current flowing through, so literally I is zero, even though that happens, the ammeter may show some reading. Let's just say that it shows it to be like 0.01 amperes in the ammeter. This is called a zero error, and that must be taken into account when you're looking at the final reading when you're closing the circuit and measuring the current. So that is a basic example of a zero error, and you can take this example to help you look at different questions in different chapters, not only the ampere or the Vernier calipers or the screw gauge, but anything else. This is the basic definition of a zero error. So here's the first example that we have right here. So this reading right here represents the reading of the Vernier calipers before the object is put inside, so when the jaws are closed, and this one right here represents after the object is put inside. So let's just erase these two and we'll get started. So first, before you actually put the object inside the Vernier calipers, when you have the Vernier calipers in front of you, you are supposed to close the jaws and figure out if there's any zero error present in the Vernier calipers. So if the zeros of the Vernier scale and the main scale are aligning, then you don't need to focus on that. You can just directly give the reading. However, if there is a zero error, then you have to consider that and put that into account when you're putting the final reading. So let's just look at this first reading. We have the main scale 0 right here. To the right of the Vernier 0, which is right here. Now, what I'm going to do in this case right here, since the Vernier 0 is behind the main scale 0, or to the left of the main scale 0, I'm gonna extend this main scale behind the 0 as well, so towards the negative side. And just took that line off. So let's see. I'm just gonna extend this line right here so that we get that. And I'm going to continue these readings. So this is 0.1 centimeter, right? Because each main scale division, write that again here, 1 MSD is 1 millimeter, right? So this is 0.1 centimeters, by the way. All of these are in centimeters. 0.2, 0.3, so on, doesn't really matter. But we'll write, we'll draw the next one to the behind. So this is, let's just say, minus 0.1 centimeters. And that's one of the main scale divisions. And since we know that when the vernier 0 is to the right of a main scale division, then that main scale division would be our main scale reading. Since we know that, we can now say that negative 0.1 is our main scale reading. So main scale reading is negative 0.1 centimeters. We got that. Now let's take a look at the vernier scale. Basically, after this, after we extend the main scale the main scale beyond the main scale 0 towards the negative side, we just follow the same procedure that we use when normally figuring out the reading. So the only difference is that we're going to get a negative reading instead. So when we're looking at the vernier, we have to check this coincidences. So 0 isn't coinciding, not 1, not 2, not 3, not 4, not 5, not 6, but 7 is. 7 looks like it's coinciding with one of the main scale divisions. So here, this is 7. So therefore, our vernier scale reading, or VSR, is VC times LC, right? Our vernier coincidence times the least count. So that would be 7 times 0.01, because our LC is 0.01, as I've discussed in the previous video. So yeah, we get this as 0.07 centimeters as the vernier scale reading. And since we know that the final reading is equal to the sum of both the main scale reading and the vernier scale reading, that would be negative 0.1 plus 0.07, which is finally negative 0.03. This is the reading initially of the Vernier calipers, which is why I'm going to name it as R1, by the way. So that's our 0 error here. So this is our 0 error. Because instead of showing 0 when both the jaws are closed, it's giving us a reading of negative 0.03 centimeters. Since the initial reading is negative, we call this a negative 0 error, or a negative error. So this error is negative. So this is a negative error. Now that we've got R1, let's try to find the final reading. Okay, I'm just going to zoom in on that. So this scale right here shows us what the reading was after we put the object inside, right? So let's look at that. The main scale 0 is right here, and the vernier scale 0 is right of the main scale 0, just to the right of the main scale 0, and hence, because of that, we know that the main scale main scale reading is 0. Why am I writing 0? So yeah, the main scale reading is 0. And now we just have to find the vernier coincidence. So let's see. 1 isn't coinciding, 2 isn't coinciding, not 3, not 4, not 5. But 6 looks like it's coinciding. Check. This is the 6th one, and it is coinciding. So 6 would be our vernier scale, vernier coincidence. And so our VSR, our vernier scale reading, is 0.01 times 6. so 0.06 centimeters. And since the final reading is MSR plus VSR, we're going to add those two and we get 0.06 centimeters, right? So that would be our final reading, which is R2. I'm going to label it as. So that we get this. This is our final reading. Now, when we get that, we have R1 and R2. A typical thing that we can, regularly while observing things, we find out that the final reading, like the actual dimension, and we're just going to write that as D, the actual dimension D is final reading R2 minus the initial reading R1. So that's important. Our actual dimension is the final reading minus the initial reading. So when we're doing that, we just have to do 0.06 minus negative 0.03, and we get that as 0.09 centimeters. So this would be our actual dimension of the object that we're putting inside. So that's the answer. Just remember that when the vernier zero is to the left of the main scale zero, it's a negative error. But usually I don't remember it like this. I just, find out the initial reading, and if the initial reading of the Vernier calipers is negative, then it's a negative reading. That'll be much more easier to remember, and you can just derive it on the spot if necessary. So yeah, this is how you can find out the reading of the Vernier scale. Not the reading, but the actual dimension of the object when there's a negative error. Here's a small side note for those of you who have been wondering how D is equal to R2 minus R1. Let's just take a look at this scale right here. So this is our object, this line right here, and now that I've put it against the scale, we know that this ends at 1 centimeter and this ends at 4 centimeters, right? So what would the length of this be? It would be 4 minus 1, right? 3 centimeters, right? So basically what I'm trying to say is that this is our final reading, R2, and this is our initial reading, R1. This is just similar to that error that we had. So R2 minus R1 would be the actual dimension of the object. So that's how we got that. Just a small side note for those of you who've been wondering. Now that we've discussed about a negative error, let's move on to the positive error. So when we're looking at this top vernier scale right here, we find out one thing. Let's just find out the reading here. This is before the object is put inside, by the way. So let's get ready. So this is the main scale 0 right here, and the vernier scale 0 is here. And since the vernier scale 0 is just to the right of the main scale 0, the initial main scale reading, MSR, is 0. Now let's find the vernier scale reading. We just have to find out at which point on the vernier scale it's coinciding. So this isn't coinciding, this isn't coinciding. This looks like it's coinciding, and it is coinciding. So this is 1, 2, 3. The third vernier scale division is coinciding, and hence the vernier scale reading is 3 times 0.01, which is 0.03 centimeters. And since we know that the actual reading of the Vernier calipers is MSR plus VSR, we can just simply write that the initial reading R1 is 0.03 centimeters. And since here our initial reading of the vernier calipers is positive, we call this a positive error. So this error is positive. So we've got that. Let's move on to the reading after the object is put inside. So we just gotta check where the vernier 0 is first. So the vernier 0 is right here. And the main scale division, which is just to the left of the vernier scale 0, is 1. So 1 is just to the left of 0, or the vernier 0 is to the right of 1. Either way works out. Just the visual representation is what we need. So our main scale reading here, or our MSR, is 1 centimeter. Now let's check the VSR. Once again, all we gotta look at is the coincidence. 1 isn't, not 2, not 3, not 4, not 5. 6 is coinciding. So this is a 6th division and it's coinciding. And so we can say that our VSR is 0.06 centimeters. Once again, 6 times 0.01. That's what we're doing here. And then obviously the reading is the MSR plus the VSR. So that would be 1 plus 0.06, and that is 1.06 centimeters. And this is our final reading, R2. I'm just going to highlight that. And since we know the actual dimension D, our actual dimension D is R2 minus R1, we can just subtract those two. So we get the final answer as 1.03 centimeters. So this would be our actual dimension D. So that's the dimension of the object that we're trying to find. So here, another thing that you could take note of is when the vernier 0 is to the right of the main scale 0, then the error is positive. Once again, I don't really advise using this memorization technique. You can always just find the reading, and whether it's positive or negative, you can figure out from that. But yeah, if you want to, you can. There's no big deal. But yeah, so this is the positive and the negative error that you can see in the vernier calipers. And it's also very important to check whether the vernier calipers has a positive or negative error so that you get a more accurate reading and also a more accurate dimension. And this could help you in different experiments, not only when you're reading something off of the vernier calipers. So yeah, that's the main theory of this part. We are going to discuss some more questions later on that have come in different past papers and stuff, but stay tuned for that. That's it for this video.